Okay. So reviewing assignment number 5. So assignment 5 was focused on another set of special class of linear optimizations, specifically integer optimizations and I guess you could say binary optimizations, okay, which are a special class of integer optimizations. So let's look down at actually problem number 3. So problem number 3 from assignment 5 has to do with assignment of, in this case, umpires to which game they will officiate. Okay, so what you have is you have 6 umpires or 6 people that need to be assigned to one and only one of 5 different games. Okay, so you have more people than games to assign them to. So somebody won't get assigned, but nobody can be assigned more than once. Okay, and every game has to have at least one, or it has to have one umpire assigned to it. And so the person in charge of this has kind of taken some historical information about how many team members playing in a certain game that umpire has officiated before. So how many times they've officiated a game with those team members. And the objective they want to optimize in this case is having umpires officiate a game with the fewest number of players they've seen before. So they want to sort of limit the amount of umpires officiating games for student or players, tennis tournament players that they've seen before. So all of that information is given here in this table. So I'm just going to take this as is and copy it into Excel. Unfortunately, that didn't work very well, but we can move that around. Okay. Let's make sure we get all that right. It seems like we've gotten, oh, okay, 1, 2. Okay, that's right. Okay. So we can worry about all the labels. Should we get all the right values? Not sure where these values came from. 1, 2. This should be a 1. Okay. That looks better. So this is the double semifinal 1, single semifinal number 1, and the single semifinal number 2. Okay, so there we go. So we have our 6 umpires, and for each match of the 5 matches, we have the number of players playing in that match that umpire has previously officiated a game for. Okay, so what we need to do is figure out a way to assign a game to each one of the 6 umpires. So the easiest way, I think, to do that, since we have the data already in tabular form this way, is we can create a matrix or a table for our decision variables. So I'm going to make those my standard orange color. And the values we will choose here are zeros and ones, okay, depending on whether that umpire will officiate that game or not. So a 1 means that umpire will officiate, a 0 means they will not. So here you'll see that of all the 6 rows, each row should have a sum of 1 or 0. That is, they can officiate at most one game, but one umpire obviously can't officiate any of the games since we have one too many umpires. So if we sum across each row of these decision variables, we want to constrain each one of those things to be less than or equal to 1. Okay? And in a typical assignment problem, you might constrain all the rows to be equal to 1, but that's only when you have a square matrix, the same number of rows as columns. So everybody has to be assigned exactly one thing. Okay? However, when we sum across the columns, that is, how many umpires are assigned to this particular game, those values should always be 1. Okay? Because you have to have one umpire, you can't have 0. Okay? So that's the setup, at least of the model, to say here's how we decide who's going to umpire which games and how we can constrain to make sure we don't over or under assign any umpires. So the last thing we need to figure out is how to represent our objective function. And the objective function was just going to be computed using our standard sum product that says take the number of players playing in the game, multiply that by whether or not, or take the number of players that umpire has seen before for that game, multiply that by whether or not that umpire is officiating that game. So effectively you're just going to sum up all the values in the top table that correspond to a cell with a 1 down below it in the second table. Okay? So in this case, the way I've assigned these umpires, just 1 to each game, the first 5 umpires, across those 5 umpires, they're basically officiating a game with a cumulative number of 13 players they've seen before. If I'd switch, say, umpire 1 and umpire 2, that objective function would then be 10. Okay, so that's better in the sense that that achieves that's a better objective for what we want to achieve, which is fewer number of players that the umpire has seen before. Okay, so that's more or less the model. Now this is a typical assignment model in the sense that we have some resources, umpires, people, whoever, whatever you want to talk about, and some tasks, jobs, games in this case, to officiate or something, and you want to assign a person to a task. You want to assign a resource to a job. You can't over allocate, that is, you can't assign a resource to more than one job. You can't assign you can't assign a resource to more than one job, nor can you assign more than one resource to a job. Okay, which in this case means we have one too many resources for the jobs we have. Okay, so to set the model up in Excel using Analytic Solver platform, we declare that this table here that I've highlighted and that was in orange is our decision variables. Okay, we have 6 constraints across the rows, each of which must be less than or equal to 1, although to make that explicit, I put that out there. And then across the columns, we also want to constrain those to be strictly equal to 1 in all those cases. Okay? So 2 different ways you can set up those constraints. You'll see how they're listed here. So cells B15 through F15 must all be equal to 1. Cell G9 through G14 must be less than or equal to the corresponding cell, 1 by 1, from I9 to I14. Okay? Neither one of these ways is necessarily more right or more wrong than the other. Just 2 different ways you can specify the information. Obviously, listing out the constraint, the maximum value out here, makes the model a little easier to see what's going on. There's less intuition or less implicit knowledge that you have to know these values here for the columns are constrained to be 1 by looking over here in the Model tab. And then finally, we'll list our objective function, which is what we want to minimize. Okay. Now, obviously, we've set it up so that we cannot put a value greater than 1 in any decision variable. That would obviously violate the row constraints. However, you could put a negative value, right? So I could put a negative 1, say here, maybe even balance that with another 1, say down here, and I'm still meeting all these constraints. That is, the sum of this row ensures that this umpire is assigned to no more than 1 game by assigning him to 1 and unassigning him from another, and so forth for the columns. Obviously not legal. So we want to make sure that we either constrain all decision variables to be greater than or equal to 0, which we can do with a normal constraint, or through the engine tab where we say we assume non-negative, and that's true. So we assume no decision variable value can be negative. Okay? That effectively creates, in this case, 30 more constraints. That is, of all our 30 decision variables, each one is constrained to be greater than or equal to 0. Okay, so let's execute the model, see what it determines. Okay, so we see the green message, it's found a solution, optimality is satisfied, all conditions are met, and we can read through here and see. So the typical question might be, which umpire was not assigned to a game? So you can look across the rows over here and see that umpire 1 was assigned to none of the 5 games. So he was the one decided to be left out, which makes some sense if you look at the values up here in the table intuitively. Every umpire has a 0 for some game. That is, there's some game that he could officiate in which he's never seen any of those players before, except for umpire 1. So he's seen all the players in every match, at least one of them before. So it kind of makes sense he might be the umpire you would not assign. However, across these umpire, let's see, is it 3 and 5, the game in which they've seen 0 players before is the same game. So you can't assign both of them to the junior match. So we had to assign, in this case it looks like umpire 5, to the doubles semifinal number 2 match, okay, which is where we actually get the single value 1 for our objective function. Everything else was 0. So minimized umpires officiating games of players they've seen before by assigning them in such a way that only one umpire officiates a game in which he's seen a player before, and of that game he's only seen one of the players, not more than one. Okay. All of those, ways you can explain either the pattern to this model or questions that could be asked about what the optimal solution is. So let's look through here. So on the assignment, construct the linear model. Do not include binary constraints. So in a binary optimization problem, you may have to specify exactly that your decision values have to be binary, 0s and 1s. There's a reason why you do not have to do that in this problem, and it's because of the way we set up the constraints. So remember, you can't have a negative constraint, but no row or column can sum to more than 1. Okay? So you could never assign a value greater than 1 by virtue of the fact that you could never assign a value less than 0, which means you're always constrained 0 to 1. Technically, we didn't say that you couldn't assign fractional values, but it would never be optimal to do so in a linear optimization problem. And I tried to explain that last week. Just to try one more time, the reason you would never want to assign, say, a fractional value is you would never want your objective function to take half of a worse choice and half of a better choice. Okay? You would want to take all of the better choice. That is, if I was deciding whether to assign umpire 1 or 2 to this second match, Right now I decide to assign umpire 2 because he's seen 0 players in that match before. Umpire 1 has seen one of those players. It would never make sense to assign half an umpire. Wouldn't make sense, but in real life, but it also wouldn't make sense in the models world, because why would you want half of a worse objective and half of a better objective mixed together? You would always want to get the best possible objective you could. Okay, and so just by definition of how linear numbers are going to work out, and obviously if you remember back to when we did linear optimization by hand, we defined that our optimal solution always lies at the boundary, okay, where multiple constraints meet. Okay, they don't lie somewhere inside the constrained region or along one of the constraints, but not at the intersection or the boundary of 2 constraints. So the best solution is always sort of the boundary between the 2 constraints, where you're actually, instead of between 2 decisions, you're fully committed to one and not the other, in other words. So in this case, the assignment said not to include a binary constraint, not because it's wrong, but because it's not necessary. Okay, and that's only true in a linear model where you're doing assignment such that you constrain no value to be less than 0 or greater than 1 by virtue of the constraints we've defined. Okay, so construct the model in a tabular form, just like a transportation or assignment model, which is what we did. So we just used a tabular form in which you had rows representing your resources, columns representing your jobs or tasks or things the resources should do, and then you had one table representing sort of the objective values, that is, what's the cost or the value of having that resource do a particular job, and then you have a separate table of your decisions where you decide which resource is doing each job. Okay. So what is the optimal assignment? We kind of talked about that. Umpire 0 is not assigned to a match. Umpire 2 is assigned to the second match. Umpire 3 to the 5th match, and so on and so forth. Suppose the objective function was reversed and we wanted to maximize the number of players seen. What is the new objective function value in assignment, and which umpire is not assigned? So we could literally just change this objective function. Instead of saying we wanted to minimize it, we could change to say we want to maximize it, rerun the model, right, and find out what the new optimal assignment is, which will be something in effect to the reverse of this one. Okay? So I would expect that instead of umpire 1 not being assigned, he would be assigned, and all umpires would be assigned to a different match than they are currently if we're trying to maximize instead of minimize, if we're doing the opposite, or trying to achieve the opposite effect. Okay? So I won't necessarily do that, but you can imagine what that would look like, and you would answer the questions the same way. What's the optimal value of the objective function, and then describe which umpires were assigned to which matches. Okay, so that's exercise number 3 from assignment 5. Let's take a look back here to exercise number 1. I did want to make just a couple quick comments on that. I took this exercise from the book. However, I obviously added a few things, but I also found the book description ambiguous. Okay, so I tried to add some extra clarification to it. So let me call that out to make sure everybody understands. So the problem is this company, Acme Alarms, either they build and make and sell alarm units. Okay, does it say what kind of alarms? Fire or smoke detectors or something like that, I believe. And there's 2 models or 2 kinds of alarms they make: a battery operated and an electrical or an electronic operated detector. So there's 2 kinds you can make. Effectively, what's going to be decided is how many of each model to build and make, okay, to maximize profit. So there's costs associated with building the models, getting the material, assembling them, shipping them, and so forth. There's a profit that you can make per model, per unit, and so you want to decide how many to build of each kind. There's also a constraint on how many are sellable. That is, the market only has so many people who want to buy these kind of detectors, So you don't want to make and try to sell more than the market would buy. Okay? And so there's limits or maximums on the number of sellable units of each kind. However, there's one final twist, which is instead of building units, you can also pay a subcontractor sort of a higher price, and they'll do all the work for you. They'll build, assemble, ship the unit, but for a higher cost than what you could do it yourself, right? Which you could pay your own workers and get it done in. So effectively, there's 4 decision variables. Okay, there's how many battery alarm or detectors to build. There's how many electronic detectors to build. There's how many battery to subcontract, that is to let the subcontractor build for you, and there's how many electronic units to let the subcontractor make for you. And you can decide on values for all 4 of those things. You could decide to build, say, 1,000 battery units and subcontract 1,000 or 2,000 units. Okay, so in effect, you would have 3,000 battery alarm units you could sell, some of which you built yourself for a certain cost, okay, and some of which you subcontracted for a different cost, okay, but you would sell them for the same amount, and so your profit, your revenue minus your costs, would be whatever you could compute, okay. So just wanted to make sure that was clear. There's 4 decisions to be made. Battery, two kinds of alarms and 2 options, building your own or subcontracting them. So 4 total decisions, numbers you'll decide. So again, all of this is set up to be a linear model. Every function should be a linear function of the decision variables, so you can build a linear model for this. This kind of problem not being an assignment or a transportation kind of model where you have resources and jobs to associate with one another, or routes between source and destinations, probably doesn't make sense to make this a tabular or matrix model. Okay, I would lay this out as my 4 decision variables in a row with 4 columns, and then you're going to multiply those decision values by different parameters to compute costs versus profits versus I think how many hours required in 3 different departments to build them, and so forth. So obviously for the models or the units you build, you have to consider how long that takes in your 3 different departments, fabrication, assembly, and shipping. For the number of units you get from your subcontractor, you're not having to do that work. So a subcontracted unit uses 0 hours from those 3 departments because the subcontractor takes care of it for you. Okay. All right. Okay. So then, just the typical questions: what's the maximum profit? That is the objective function value in the optimal case, and what's the corresponding make and buy levels? All I mean is how many units did you decide to make of both types? How many did you decide to buy or subcontract of each type? Okay, so 4 values that we've decided on. If you had the option to increase capacity of one of those departments, which would you increase and why? So presumably, the hours available of one of these 3 departments, 1 or more, might be a binding constraint, might be preventing you from making more units. And theoretically, you should want maybe to increase that capacity so you can make more units, right? Then using the pattern in A, so whatever you computed from part A, trace the effect of increasing the fabrication capacity by 10%. So, just as an example, if you decided to increase the shipping department available hours, if that was a binding constraint, they currently have 2,500 hours. Let's say you could increase that by 10%. So increase it by 250 hours. Okay, so then that shipping department would have 2,750 hours available. What would the new optimal decisions be? Okay, so that's part D. Part E, for how much of a change in fabrication capacity will the optimal profit change? So let's assume you were changing fabrication capacity. Basically, I want you to do something like optimization sensitivity to say how much can you increase that by, increment by increment, until you no longer are getting a better profit. You're no longer making different decisions. So maybe you increase it by 100 hours and you make a better decision, better profit. You increase it by 200, it makes a better profit. But once you increase it by 300 or more, that constraint is no longer binding, and it no longer helps you achieve a better optimal pattern or better optimal profit. Okay? So that's what those 3 or 5 parts are asking. Exercise number 2, somewhat similar. This is a binary model in which you're deciding yes or no which of 8 projects to undertake, but you're constrained from selecting all 8 by the number or the amount of money it costs to undertake the project, for which you have a maximum budget, and the number of scientists or people it would take to work on that project, of which you have a maximum number of people. The objective is to maximize the profit of these selected projects. And then most of the rest of these parts, in addition to asking about binding constraints and such, involve adding new constraints that are either mutually exclusive constraints or either or kind of constraints, mutually exclusive, or you have to select a minimum number of certain subsets of the projects and so forth. So adding additional constraints to the problem, re-optimizing, okay, to find the new optimal answer. Just to ask, if I did this project or I did this exercise, found that, say, my optimal profit was a certain amount, say $100 or $100,000 or whatever it is, and I added a new constraint, would the new optimal solution with the added constraint, would you expect that to have a better or worse objective, a better or worse profit?
Worse if it's changed.
Worse, yeah. Worse. So if that constraint is violated by the current best solution, we're going to have to change that solution, re-optimize, and by definition, it's more constrained, so we're going to get a worse profit. That is, you can't add constraints and do better. Now, you might add a constraint that doesn't matter, isn't binding, in which case you can do the same. But generally speaking, if you add a constraint to the problem, you're going to get a worse optimal solution because the solution is being constrained even more than before. Okay? So generally speaking, just as a check while you're doing this project or this assignment, you might consider that every time you add a constraint and re-optimize, theoretically, you should never get better, and more than likely, you should probably be getting a worse or a slightly worse optimal solution, okay, than before. Okay. Any final questions about assignment number 5? So, yes.
So when can we? So it's due at midnight on Saturday.
Yes.
Will we get our grades before?
Yeah. So good question. So this assignment's due Saturday night. The final exam is a week from tonight, next Thursday. I will get these graded sometime early next week, so sometime Monday or Tuesday or so you can get feedback on how you did or what you did wrong, if anything, and so forth. Speaking of, I don't know, I assume you've noticed, but on Blackboard, when I assign you a grade, if it's not 100%, I usually add a comment saying what you got wrong, how many points were taken off for different parts you got wrong, and so forth. So if you're ever curious about why you might not have gotten full credit, I generally try to explain that on Blackboard through the feedback or comment section. So for this assignment, right, this assignment's due before the final. I will have it graded before the final, a few days before the final, so you can get feedback on it. The assignment we will be assigned tonight for the new topics we discussed tonight won't be due until the final exam or the night of the final exam at midnight. So theoretically, you could come to the final exam having not done that assignment yet. If you get it done early, okay, say by Monday or Tuesday, I will do my best to grade it for you so you can get feedback on it. Okay, so especially if you're unsure about the new topics we learned tonight, I would encourage you to try the assignment as early as possible. Go ahead and submit it, and I'll do my best to grade it. okay, so that you can know whether you understood and got it right and so forth. In addition, okay, I promise to try. I can't promise I'll get everybody's graded, especially if you submit it late Wednesday or something like that. Generally speaking, if you can get it submitted early, I can get it graded early, and you'll still have time to resubmit it, okay? So you can even, right, see what you did wrong, fix it, resubmit by the deadline, and get a higher grade, okay? A few people, by the way, have done that this semester, not many, but most people submit, right, the last day. A few people usually submit 3 or 4 days in advance, and as I have time, I try to grade those, give feedback, and they've even resubmitted, okay, and got some credit back, okay?
Oh,
So-
I do that sometimes just because I'm worried my laptop might crash. And
Even a better reason to get it done early, just in case something goes
Oh,
wrong.
no, I'm not
or
actually done. I'll be like half done. I'll just submit it just because I'll be like,
Oh, okay.
You know, hey, I did get hit by a bus, but at least I'll get half credit.
Oh, I see. Yeah, so there's nothing wrong, with submitting half the work early and then the rest of it later. Generally speaking, if I go on to grade and you've had 2 submissions that I hadn't yet seen, I'll just grade the last one, assuming that's the full one, okay? And only if it's wrong in some way do I even really look at the other, if that makes sense. So I generally try to cut down on the amount of work I do, but I always grade the most recent thing you submit, and only if it's missing something do I go back and look at your other submissions. So, again, assignment 5, I'll submit it by Saturday night, the due date. I will grade them Monday or Tuesday next week, get feedback to you. Assignment 6, if you do submit it early, I'll do my best to also grade it and give you feedback. But it's not technically due till after the final exam, which is unfortunate, but just the way the schedule works out when you have a course like this one that only meets once a week for 7 weeks. So another question.
I had a question on this problem.
Yes.
On Part E, it says, in addition to the condition imposed in Part C.
Mm-hmm.
And I didn't see a condition imposed in Part C, so I did that as Part D.
Oh, yes, you're right. So this should actually, so Part E should say, in addition to the condition imposed in Part D.
And then it would be the same.
And then, down here it should be D and E. Yeah, I didn't notice that. Wow. That's me miscounting or mislettering. Yeah. Effectively, these last 3 parts are each adding an additional constraint, and I just wanted to make sure those were all cumulative. What I found in the past, if I didn't say that, some people assumed they were cumulative, some people assumed they weren't, so people were getting different answers, and I had to give credit for both. So this time I wanted to be clear. Once you do Part D, you're going to add Part E to that. And then once you get that done, you're going to add Part F to all of that. So you'll end up with, by Part F, you'll end up with something like 5 or 6, depending on how you count, constraints total. Yeah, thanks for asking about that. I'll make sure I correct that maybe for the next set of students. But okay. Well, that takes care of assignment number 5 and linear optimization. So just kind of briefly recap. Linear optimization, we talked about some general linear optimization problems. We did some special classes like transportation models, assignment models, transshipment models, okay, which were all kind of forms of network optimizations. And then we looked at integer and binary linear optimizations. All of that is linear in the sense that the objective and the constraints are linear functions of your decision variables. In the case where you have a constraint that's not linear, a non-linear function, some of those, we talked about a special class called blended constraints, where you're doing sort of a ratio of your decision variables. So sort of the percentage of one out of the total of the decision variables. You can manipulate that to be a linear function. So we practiced that, saw how that worked. And in that way, we can make that a linear optimization problem instead of something different, okay? Unfortunately, this semester we didn't have time to talk about the alternatives to linear optimization. There are some. There are ways you can do optimization even if your functions aren't linear. effectively what you have to do is you sacrifice the guarantee that you will find an optimal answer in exchange for being more expressive and flexible and allowing more kinds of functions. Okay, so what a nonlinear optimization problem or solution would get you is a near optimal answer. Maybe optimal, but not guaranteed. But I won't say guarantee is a strong word. It's promised to be close to optimal. Okay, in exchange for being able to use nonlinear functions like square roots or logarithms or ratios and divisions and other things like that of your decision variables. So we didn't do anything like that. There won't be anything on the final about that. I just wanted to make you briefly aware that, just time constraints. We studied what we did during this term. I just want to make you aware that there's plenty of other things out there, okay, beyond what we can learn. Many of which are covered in the textbook. You can read about there, but even beyond the textbook, right, there's still other methods and other things in the space of operations research that you can learn about. So, okay, well, let's take just a short break. We'll take a 5-minute break and then come back and talk about what will be the last topic for the term, which is simulation.